Hi, everyone. Thanks for coming out this morning. My name is Forrest, and I'd like to talk about a new method for predicting the optical brightness of satellites. So obviously everyone has their own slide about brightness mechanisms, but basically when sunlight hits the satellite, if the satellite is near the terminator, that light can be scattered onto observers on the nighttime half of the Earth. Most of this talk is based on our paper, Satellite Optical Brightness, which we just published. And in the paper, we do discuss Earthshine, where light scattered from the daytime portion of the Earth's surface is scattered by the satellite, but it turns out to be a fairly small effect, and I'm just going to leave it off the table for this talk. And I want to start with one of the most useful parts of our paper with respect to thinking about satellite brightness. Let's see. Is that better, Tony? Okay. So we actually came up with this reference frame, which we call the satellite-centered frame, or I sometimes just call it the brightness frame. And it's really helpful in reducing the dependent variables that we think about with respect to brightness. So in this reference frame, brightness distributions are only a function of the satellite's height and the satellite's angle past the terminator. And this is really helpful because most LEOsats operate in circular orbits. So you can make some metrics like peak brightness or average brightness on the night sky a function only of the satellite's angle past the terminator. Which I think is really helpful. And then I would also just throw out that this reference frame is very intuitive and you can answer a lot of questions about brightness using like hand calculations and high school geometry. So I would just really recommend that you at least try using this in your future research. So I want to talk about how we decided to model satellite brightness. Ray tracing is sort of the obvious solution, but it's not a good choice because it's computationally extremely inefficient. So instead what we do is we add up the bidirectional reflectance distribution functions of every primary surface on the satellite. So the BRDF measures the scatter properties of a surface. You could have a shiny piece of aluminum or a diffuse piece of paper or anything in between. So this BRDF measures those different material properties. So you can see here we have the BRDF of the chassis deck and the solar array for Starlink V1.5 satellites. And what we do is we actually fit measured BRDF data to analytical, empirical BRDF models. And then we can use those models to calculate satellite brightness at an observer. You throw in like an inverse square law and some cosines, go read the paper. The details don't really matter. And I think what's really interesting is we actually found two ways to get these BRDFs, which are both really useful in their own right. So one way, which we're showing here, is you can just take laboratory measurements of the surface to get the BRDF. And so SpaceX provided these measurements, which we were able to fit. But then sort of after we had already done this, we realized if you have enough observations of satellites on orbit, you can sort of indirectly infer the BRDFs of the satellites. So this is really helpful because it gives us an avenue to calculate satellite brightness when constellation operators aren't feeling cooperative. So I'd like to just get right into talking about our results. We decided to validate our models using Starlink V1.5 because there's plenty of observations out there, and we had great collaboration with SpaceX to get some of the numbers we needed. So our brightness model consists of two primary surfaces. We have the solar array, which mostly drives backscattered light. So that light is going to be more visible for observers near the terminator. And then we have forward scatter from the chassis deck, and that's going to be visible to observers farther into night. So I want to start with the old brightness calculation method. This is the diffuse sphere model, and I'm a big proponent of just throwing it out. It's sort of, physicists love a spherical cow model, and this is that for satellites. It's not very physically based, but I'd like to use it for the sake of comparison and sort of explain these plots. So we have the sun altitude increasing from left to right, and we've fixed the sun azimuth at 90 degrees. So you can think of this as what an observer is going to see if they were standing at the equator during sunrise. And the color shows the brightness a satellite would be if it was at that point on the sky. So the center of these plots, that would be straight overhead. And then the top of the plots is going to be the northern horizon. And to the left, you have the eastern horizon. So you can see the spherical model is quite simple. And satellites these days are a lot more complicated than this. Maybe it worked for asteroids, but here's our new improved model. So this is our model with laboratory measured BRDFs. And you can see that as compared to the diffuse sphere model, we actually have two separate lobes of brightness. So deep into night on the eastern horizon, you can see that light being specularly reflected from the chassis. And then as the sun rises in the western sky, you get this lobe of brightness backscattered from the solar array. And hopefully you're already thinking about the applications to LSST. I mean, you can imagine streaks that get bright and then dim and then bright again, and we're going to have to be able to handle those cases. Next, I'd like to also show our model where we fit our BRDFs to a bunch, like 2,000 satellite observations from the Pominus Observatory. And you can see that it's sort of in between. I don't have a great way to back this up, but I don't think this is quite as accurate as the lab BRDF models. But luckily, we are still getting some of the features we're looking for. So we have forward scatter from the chassis and backscatter from the solar arrays. And luckily, we can back this all up with data, once again, from the Pominus Observatory. So what I'm plotting here is we have the measured AB magnitude from the observatory versus the calculated AB magnitude. And you can see that our model with lab BRDFs has fairly good correlation, but it systematically underpredicts brightness since we're not modeling every single component. We only take two primary surfaces. And then as expected, our model that's best fit has fairly good correlation and fairly good bias. And then you can see that the diffuse sphere model doesn't have great correlation and is not physically based. And I just want to highlight that the V2 satellites will not have this contribution from the solar array as strongly since they're off pointing the solar arrays, which will actually make this diffuse sphere model less and less accurate. So I think, expect this correlation to be even worse in the future. And that sort of highlights the need to move to these new models. I'd also really want to drive home that our model with lab BRDFs has no on-orbit measurements. So we actually can make a correlation like this for a satellite which doesn't exist in space yet. So that brings me to some of the applications of this paper, which aren't fully thought out. But one that I'm really excited about is trading satellite design where brightness is a constraint. So SpaceX actually used this computational technique to inform brightness mitigation for their V2 satellites. And what's really great about this is unlike any of the other satellite brightness modeling attempts I've seen, we don't require any on-orbit observations. So you can get this feedback loop where you're going from design to brightness calculation and back without ever sending a satellite to space. And then of course, we can predict satellite passes more accurately. So this is for Tucson tonight at 10:30. And we can predict fairly accurately that we should see a peak brightness of 5.3 AB mag in the eastern sky about 45 degrees above the horizon. And then you can obviously extend this to LSST. I want to emphasize that this is a toy constellation model with 30,000 satellites and a toy brightness model meant to represent Starlink V2, but this isn't published. Don't take this as absolute truth. And so we looked over a period of a 60-second exposure, and we see these 7 streaks visible in the detector. And I think what was especially interesting about this analysis is we see that the brightness of streaks can vary by a factor of 2 across an image. So that already kind of informs you whatever streak removal algorithm we have needs to handle this case. And then I think going forward, Tony's group is working on something really exciting where we combine satellite brightness models, a constellation model, and the LSST observing schedule to generate images with satellite streaks and without satellite streaks. We can then pass both data sets through the data management pipeline and come up with overall scientific impacts of satellite constellations. So this is kind of what we're looking for regulation, where you can say, if you have these 50,000 sats with this brightness distribution, here's the science we would actually lose. So for our starting effort, take a look at Fan's poster. It's really interesting. That's all I have for today, but if you're interested in this, please check out our paper. And I'd also just like to say that none of this would have been possible without collaboration between SpaceX and our astronomy team, and I would really like to see more of that collaboration in the future. Thank you.